using radicals. We can't have a radical in the denominator. So we got to figure out how to get rid of that. How do we do that? Any suggestions?
Use the table.
Yes.
Yesterday we looked at just multiplying these together, and in order to do that, what has to be the same? There's two things. Both start with R.
Radicalize.
The root and the radicand must be the same. There we go. Got a lot. Concrete little stick. N and X. This is the root. That's the radicand.
That's
And you can also have an exponent inside of there to still deal with this, even though it looks complex. And we can just move that outside. But what if you have this in the denominator and you're trying to add or subtract or work with this in an equation and you don't have the same thing in the bottom? How are you going to combine them? Well, just like when we are trying to find like denominators in other problems, we're going to have to try to find the like one like these. So we're going to look at the example really quick on page 14. It gives you square root of 5 over square root of 3, and you're supposed to do something with that.
Don't worry about that.
And then it says equals square root of 5 over square root of 3 times square root of 3 over square root of 3. This does seem like the obvious step you would take, because what happens when you multiply square root of 3 times square root of 3? If you're just simply, your goal is I need to eliminate the radical from the denominator, this will do it. The square root of 3 times square root of 3 is just going to be 3. So I have 3 in the bottom by multiplying those two together. And then on the top, it's square root of 5 times square root of 3. Can I combine those?
Yes.
In this case, I can, because I'm multiplying, not adding. So what happens when I multiply is I can just simply remove that, put them both underneath, and multiply the interior, and then I get square root of what?
15.
Square root of 15 over 3. That makes sense. What if there's something more complex in the denominator? Meaning you've got maybe an addition problem there, or subtraction problem. They've written it out here for you in terms of A's and B's, so it's worthwhile to look at that example and maybe explain what's going on. Now, if I want to fix this denominator, meaning get rid of all the radicals, I can't just multiply by square root of A. I can't multiply by square root of B. What can I multiply this by to remove the radicals from the denominator? Well, if we look at our example, it tells you can multiply it by square root of A minus square root of B over square root of A minus square root of B. Now, just so that we were saying it out loud to make sure we're understanding, how can I multiply this fraction by that fraction?
Can cancel.
How can I do that? How can I multiply something by something else without changing it?
Reciprocal.
It's like, I can't change this, it'll change the problem. But this is just equal to what?
Itself.
1.
1. So I can multiply anything times 1 because it doesn't change it. So I'm allowed to do this step without changing my original fraction, at least what it's equal to or equivalent to. And if I think about this for a moment, if I'm multiplying that times that, which is what I end up with in the denominator, and I were to FOIL this out, what do I get? I would get the square root of A squared plus square root of BA plus square root of BA, minus, and then minus square root of B squared. Does that make sense? Let's go through the steps to make sure this looks like it makes sense. So square root of A times square root of A, square root of A squared.
Okay.
I understand this is A, but just for purposes of following the logic here. Next, square root of b plus square root of b times square root of a is b a, like that. Minus b times a, so we're now doing our outside. I know we're supposed to FOIL, F-O-I-L, but I did the I first. The outside is this, right? Negative b, a. And then here, negative b times positive b is negative b squared, the square root. When I simplify this, I'm just going to get what? A. These two cancel, because one is subtracted from the other. This is just going to leave me with b. So that will become my new denominator, a minus b. The top part, though, doesn't work out quite so easily because they're both subtracting. So I'm going to end up with a much larger problem. You can see that worked out there for you in the example.
Yes, sir.
You end up with these two multiplied by each other, which is going to give you what? Let's go ahead and erase this step that we wrote, and now deal with the top. Now we're just dealing with the top up here, and we'll write it here. So square root of a times square root of a, let's go ahead and simplify that to a. Next, to do the outsides, I would have negative square root of ab, and then negative square root of ab again, and then positive, because if it's negative b squared times negative b, square root of b rather, negative square root of b, that's going to give me positive b on top. And when I combine these two together, remember what do we do?
Negative 2.
So combining this negative 1 with that negative 1 to get a negative 2, so negative 2, and this part would go away. It's absorbed in here, so a minus 2 square root ab plus b. And that's how I would simplify that. So this is the format you would use in the problems that you could have numbers. So you would do any of those with some numbers. You see 1, 2, 3, and 4 on the bottom of page 14? Those are just like the simple example at the top where you just simply multiply the top and bottom, or really you're multiplying the fraction by 1 because it's not going to change it. So you multiply the top and the bottom by the radical that's in your denominator. So that way you can eliminate that radical from the denominator. So we won't do any of those. But look at the next page. We definitely want to look at number 5, just for practice, because I really like number 5. Wow! That problem is square root of 7. This marker is really dying. Square root of 7 over square root of 12x. If this were a commercial for expo markers, no one would buy any because these just aren't lasting. I don't know what's happening. So not going to get a sponsorship there. Nope. So that's square root of 7 over square root of 12x. Remember, we're looking for anything we can do to simplify. So yes, we could just multiply by 12x, square root of 12x on the bottom, but is there anything I can do to simplify that just a little bit, just a wee bit first? So what I mean by that is you want to look at any number that you have and see, are there any factors that are square rootable? That's always one of the questions you want to ask yourself. And so, I'm asking you, are there any factors of 12 that are square rootable? And you would say, yes, 4. So for now, just take the step, leave the whole thing on the top. So this is square root of this. We can split the 12 into its factors. 4 times 3 times x. And we know that these can also be dealt with individually. Square root of 4 times square root of 3 times square root of x. So square root of 4 becomes, square root of 4 becomes 2 square root of 3x. Square root of 7 stays on top. That's just a little bit easier number to work with, but now what do we do to simplify that?
Can't really simplify it.
Well, we gotta get rid of this in the bottom, so how do we do that? So
Sounds
we do
about
like we
right.
did on the other step, we're gonna multiply this whole thing by 1, but in this case, 3x over square root of 3x. Because this is still equal to 1. Multiply these two together is gonna give me what?
9x squared.
So this times this is 2 times what? 3x. Because it's 3x, square root of 3x times the square root of 3x is just going to basically eliminate the square root part.
So it's 6x.
And that's going to end up being 6x on the bottom. Now, back to the top. I have square root of 7 times square root of 3x.
21.
So this is going to give me square root of 21x. Does that now give me any factors that are square rootable?
Yes. Gross probably unsolvable.
Well, that could be our answer, square root of 21x over 6x, but can you do anything with 21? What are its factors?
9 times 3.
We know it's 7 and 3.
It's 20.
Did you say 9 times 3?
No, well, we don't.
Aiden didn't say that.
Any factors of 21 that are square rootable?
No.
No, there's not. So we are done. So square root of 21x over 6x. That's what you would circle, call it done. Let's stick a fork in. Now let's jump down to number 9. I also really like that problem. What is number 9? This one we'll get to employ some of the newer method. We're going to really like this one.
Isn't it like -1 over -7?
Alright, so to start out with, can't I just cancel these? -3 and square root of 3?
Yes.
No.
Hallelujah.
No, we can't. So we have to deal with them, and we need to get rid of that. What do you think you should do?
Times by 3.
Negative square root of 3.
Multiply 3 over 3.
Square
Square root of 3 over 3. Let's go.
Well, if I do that, then it would eliminate this one, but then it's going to stick a square root of 3 in this term, and that doesn't help me. So, we take this, and we're going to multiply it by, this is going to become a factor, we're going to multiply by 2 plus square root of 3. Now, where am I getting this format? 2 minus square root of 3, 2 plus square root of 3. Remember, those were the perfect square factorials that we were working on.
Why wouldn't you just do it by 2 minus square root of 3?
Because then I'm going to still have square roots in the bottom. 2 minus square root of 3 times 2 minus square root of 3 is going to give me 2 times 2, which is 4, and I'm going to get -2 square root of 3, -2 square root of 3, plus 3 at the end. So then I'm going to end up with this -4 square root of 3 in the middle, still not making the progress that I needed to. When I turns that to a positive, that changes one of these to a positive, eliminates the terms in the middle, and I end up with 4 plus 3 in the bottom.
Yeah.
That'll be 4 plus.
We can go through that a little bit slower. So 2 times 2, 4 is 4. 2 times square root of 3 is plus 2 square root of 3. 2 times negative square root of 3 is -2 square root of 3. Negative square root of 3 times positive square root of 3 gives me -3. Right? The square root of 3 times square root of 3 is going to be 3, just like here. 2 times 2. Make sense so far? So that's my new denominator. And these are going to go away because they're going to cancel. Plus and minus in that case. These are both in the denominator, so yes, I can cancel those. I'm not dealing with anything in the numerator. What am I multiplying the top by? Same thing. Because I need to multiply this whole thing by 1 to keep it equivalent. So we'll start out, same thing. 2 times 8 is 16. 8 times is plus 8 square root of 3. 2 times negative square root of 3 is negative 2 square root of 3. And then minus 3 on the top. I see those minus 3s hanging out there. Can I just go ahead and cancel those?
No.
No, do not do that. This is equal. So now continuing on. In the denominator, I have 4 minus 3, which is
1.
1. Oh, that's great. Up top, I have 16. So let's just, for simplicity's sake, let's leave that. Let's deal with the more complex part first. So I have positive 8 square root of 3 minus 2 square root of 3. Can I combine these two? I can. So
Yeah,
I'm
we did.
essentially going 8 minus 2, which is plus 6 square root of 3. So the square root of 3 here is sort of carrying me along like a variable because I can combine them. The root and the radicand are the same. And then my minus 3 is out in the end. Now I can go back and deal with the 16 minus 3, which is what? 13.
There.
So 16 minus 3 is going to be 13. So I'm going to have 13 plus 6 square root of 3.
Over 1.
Over 1, but the over 1 part can go away. Now, anything I can do to simplify that any further?
Nope. No.
No, it's as simple as it can get, and that will be your answer. You would write that in a blank and circle it. And those are the two types of problems we have on that page. You see, that's the same thing we would do for number 10. Only they just gave you the x's and y's, but I think that's almost virtually identical to the example from the other page. Number 8 is the same thing, only the numerator is slightly less complex, so that's why we skipped that one. Number 7 is the same as 6, is the same as 5. You handle all those the exact same way. You're going to multiply by the denominator, 1 over 1, the equivalent fraction of that. The next objective is we're converting radicals into forms with exponents. We reviewed this just the other day briefly. So I'm sure you remember that n square root of x with an exponent m can also be written like this. Well, we also know that this can be written how? X as 1 over n, right?
Mm-hmm.
Just that inside. And then m out here, which makes that x to the m over n as your exponent. So you can write that like this. Which one feels easier to deal with?
Without 1.
I think probably this one, just because that radical sign, it's hard to manipulate radical signs with other things. They're not very compatible with each other. So why not write it like this? And then I'm just dealing with something that has this crazy exponent, but at least it looks like something I'm more familiar with. And if this was in terms of a number, the example they gave you there is 4, or the 4th root of 17. Another way I could write that would be what? 17, and then what would be my exponent here? What would go there? Well, look at where the n went. The n went to the denominator part. The n went to the denominator part. So the n here is 4. The m is the top part. What's there?
1.
Just a 1. So I can write this as 17 to the 1/4 power. And those are the same. So don't get tripped up by, oh, what is my exponent again? Just look at where does the n go? The n, which is this root, goes to the denominator in your exponent fraction. And then anything on the inside is going to go to the numerator. And if there is not an exponent there, it's just going to be 1.
Can't you also write it as 17 and negative 4? With negative 4 to the power?
Negative 4? Well, there's not a fraction here initially.
Oh, okay.
If we had a fraction, then you could use that.
Alright.
Meaning like this, like 17 to the negative 4 is equal to 1 over 17 to the 4th.
Yeah, that's what I was thinking.
Good. Yeah, that's a good thing to remember. Negative exponents, fractional exponents, think we'll ever have imaginary exponents?
I already have imaginary exponents.
Maybe we will. So if you're looking at that example, they turned that cube root of 9abc to just writing it as 9abc with an exponent of 1 over 5. Then I can put that exponent on each individual term since they're all multiplied by each other. So 9 to the 1/5 power, a to the 1/5 power, b to the 1/5 power, c to the 1/5 power. And if you need to separate those out, that's another way you can simplify that. Or at least you're writing an equivalent. I don't know which one's simpler, but it's definitely an equivalent. So it shows you ways that you could use that. If you ended up having something crazy like that, and that whole thing was in the denominator of some term you're trying to work with, that's how you can simplify it out, and you would use a negative exponent in that case. The example they gave you was 3 over cube root of 2. Ew. 3 over cube root of 2, which another way I could write that would be 2 to the 1/3, right?
Mm-hmm.
But this is now in the denominator. So if I want to eliminate that whole fraction, I can write this as 3 times what? Thinking in terms of the negative exponent we just used, what would I write?
3 over 2 1/3.
2 to the negative 1/3. This may be useful because this feels like something I can work with in a problem a whole lot easier than that, right? This doesn't feel like I could use that as easily. So this would be simpler to use, and they are equivalent. So looking at the next page, looking at problem number 2, what would you do to solve that one? Now we're on page 16.
Just trust your little calculator.
1 over, and now we have square root 3xy to the 8th. Well, what do I get? Leaving the fraction in place for a moment, I could write this as 3xy, and then what would be my exponent? Remember, the root goes to the where? The denominator. So
It'd be 8 over 2.
Now, since this whole thing is a fraction with 1 on the top, I can also rewrite it as 3xy negative 8 over 2. What were we doing? Number 2?
Yeah.
However, can I simplify that any?
Yes.
In what way?
You can turn the 8 over 2 into 4.
Yeah, that's still a number that I can work with. It's a fraction of 8 over 2. 8 over 2 is 4.
1 over 81.
So that means I can write this as 3xy to the power of negative 4. That's definitely simpler to deal with. Now, since we are practicing writing out the distribution of this exponent, what I can write for my answer is 3 to the negative 4, x to the negative 4, y to the negative 4. We're practicing writing it out that way so we understand that these are equivalents. Now, can you do anything more with that? I mean, maybe you could go
simplify
ahead
it.
and do that. So what would that be? What is 3
81.
to the negative 4th power? 91, but what?
9. I would find that.
Throwing out random numbers now?
Nope. It would be
1 over 81.
0.01.
1 over 81. So, for my answer, I could write this how? I could leave this x to the negative 4, y to the negative 4, all over 81.
Yep, let's go ahead.
Or could you do it like 1 over 81 x to the 4th, 1 to the 4th?
Yeah, wouldn't they have to be 1 over 81?
You said that's what I had.
Well, so if we did that, essentially there would be no point in doing all the middle stuff, because we could have just wrote that from here.
So you're telling me you're ignoring a shortcut?
That's kind of what I'm doing.
Well, we don't want to have these variables in the denominator just in this particular case. This is just, these are all various ways you can write the answer. This way, that way, this way, These are all equivalents. So those are all acceptable answers. I'm not sure which one's going to show up in the score key. I would guess maybe one of these two. Number 3. Number 3 is a nice simple one. 1 over 4th root of 5. When I practice writing out my steps, this is 1 over 5 to the what? 1/4?
Yep.
Or negative
Which
4 over
becomes
1.
5 to the 1 over -4. And that's as far as I need to take that.
Give me a decimal.
No, it's 2/3.
Hmm?
You can do more.
What more would I do?
5 to the power -1/4. Like that. What's in it becoming 2/3?
Not turning that into a decimal, that's not something we're going to do today. Now, number 6.
You just multiply them.
Isn't that 3 over square root of 6?
You end up with square root of 2 on the top. So the square root of 2 on the top, we're learning we can rewrite that as 2 to the 1/2. In the bottom I have square root of 3, so we're learning we can write that as 3 to the 1/2. If I also rewrite this as 2 to the 1/2 times 3 to the -1/2, can I do anything more with that?
Yes.
Yes.
Good multiplying.
You can't,
Okay.
because while your root may be the same, your radicand is not, therefore they cannot be combined.
Beautiful.
And then, you can see here there's nothing you can do. It's 2 over 3. And you have these fractional exponents. That's as far as you're really going with that. Alright, next, looking at the next section. So that's all we're going to do of those for now. For your extra test practice, you'll want to work on some of those other problems just to make sure that you got it.
Yes, sir.
The next objective is solving equations containing radicals. So now we've just been practicing the little parts that you'll use. So solving equations just basically means take everything that we just applied and just use that to simplify an equation and solve it. So this is an example that's worked out for you there on the bottom of page 16. Shows you how that if you have some kind of radical with a radicand that involves addition, exponents, coefficients, all those things, anything they throw at you, set that equal to something else, and you just simplify your radical and getting it to a point where you can get that, get an answer for x, or whatever your variable might be. So there's a couple of examples actually. There's another a little lengthier example given to you at the top of page 17. So let's look here and see if we can't work a problem or two on page 17. And if we need to refer back to the examples, we can move back those later. So starting with problem number 1.
62. That's the right answer.
First of all, what steps are you taking to get that?
You gotta move that 3 over, make it 1 over 3.
You'll move a 3 over, what does that mean?
Make that x plus 2 in parentheses and put 1 over 3.
Now think about the old days when we were solving equations. Maybe we ended up with square root of x equals 4. And you gotta solve for x. What'd you do?
The x equals 2. You got to square root.
Squared
4.
both sides, right?
Yeah.
And you knew that that would give you an x, and this would give you 16.
Like squared. Wouldn't it?
X is not squared. The square root of x, if you square it, that's x.
Oh, yeah.
Square root of x times square root of x, which is x. But you square both sides. So when you're faced with a problem like this, what do you think you do?
Cube.
You cube both sides, sure. So we'll cube that side,
Oh.
and so just like the square root of this would give you what it would just give you the radical, the radicand is all that would be left. Same thing here. So x plus 2 equals 4 cubed.
X equals 62.
This gives you 64. You do minus 2, so minus 2 from that gives me 62, and x is 62. So it is 62, but you need to know how you get there using a manual method. You can plug that into your calculator only after you know how to do it manually. So problem number 2 would be done the same way. Problem number 3 would be done the same way. In fact, every one of these is done the exact same way. You're either squaring both sides or cubing both sides, depending on what the root is of the radical that you've been given. So let's move on from that. The next page is where we begin our checkup. Checkup time. Now some of this is just memory, but this is an excellent checkup for study, for test preparation, for practice. Virtually every problem you're going to see again in this, as far as at least the type of problems that they're presenting you with. So you want to know how to do each and every one of these sections. So looking at the first section, find the product or quotient of each given expression, give only one positive root. So we're looking at the directions to see that I don't need to write positive or negative for my answer.
18.
So on the top one, square root of 36 times square root of 9, I know that I can combine those two, or I could simplify them out, or I just realize, oh wait, those are both square rootable.
18.
So what's the square root of 36?
18.
6. What's the square root of 9? 3. 6 times 3 is
18.
Nice. The next one is a quotient of 2
7 over
radicals, but you realize both of those are square rootable, so you get 7 over 4. And can you simplify that any?
Yes.
I mean 1.75. Hey, a decimal.
1 and 3 over 4.
Or 1 and 3 over 4 for mixed number. Yeah, those are all equivalents. Alright, number 3. They tried to trick you, but can they? No, they cannot.
Nope. The answer's 3.
Number 4. This direction says find the sum or difference of the given terms. If they cannot be combined, though, you must write y. The CBC and y. Cannot be combined, CBC and y. So what about number 4? Can that one be combined?
Yep.
And then what do you do?
Yes.
It's 9 square root of A.
So I see that I have an a square root of a plus square root of a. So that's a 1 in front of that square root of a. So the 8 and the 1 combined to make it 9 square root of a. And then can I do anything with that minus cube root of a? No, that's still just there. Number 5, can that one be combined?
Can we combine?
No.
Why not?
Because no
The roots
sum
are
is-
different.
All the roots are different. You would write different roots. CBC.
Would there ever be any other reason? Oh yeah, there is a mixed one.
The root and the radicand must be the same. In that case, the radicand is the same, the 19, but the roots are different. The roots may
So
all be the
4
same,
square
but
root
if
of
the
9
radicands
plus
are different, you
square root
cannot
of
combine them.
Easy.
Number 6.
4.
That one you can.
Square root of 11.
Sure, it's 6 minus 2 plus, oh, so just 6 minus 2, that's 4. And then the square root of 13 is left out there on the end. Now 7 is where we start just doing our simplification steps again. So the 7 through 10 section. You look at these and you see all kind of different things. So I need to start using my thought of, look at the radicand. Are there factors that are square rootable? I'm looking for square rootable factors. Are there square rootable factors of 20? Sure.
Yes.
Number 4. 4 times 5 is equal to 20. So that first step is going to turn in from this to being 2 times the square root of 4 times 5. I can deal with these individually as square root of 4, square root of 5. So square root of 4 is 2, so it's 2 times 2 square root of 5. Simplifies to this. And you would deal with each one of your terms individually and then combine them all at the end if they can be combined. Did you find that they can be combined at the end? Did you end up with a bunch of square root of 5s?
Oh yeah.
I bet you did, then you combine them to get what for your final result?
2 is square root of 5.
Yeah, they can.
Simplifies down to that, right?
Yeah, just give me that.
All right, how about number 10? Square root of 98. What are the factors of that? Square root of 98. Any factors there?
Yes.
Yes.
Yep, so we know that that's 2 times 49. 49 is square rootable, and so we can deal with that, deal with 18 as well. Number 11 and 12 are the exact same things we just covered in the earlier lesson at the start of class. We won't go over 11 and 12, although the 11 and 12 in particular are very good problems to practice with. And then 15 through 22 section are just simplifying the exponents, again, what we just did in the previous section. And then you can finish out the very top of page 19. Solve the given equations for x. Check your answers on separate paper, should you need to. And again, the directions say use only positive roots. Now we're just solving the equation. So let's look at number 23.
What do you want us to do with
So I'll give you all the numbers that you want to do. You want to make sure that you finish out this entire checkup for homework. So we're skipping around right now just so we can get the examples in. 23 is 6 equals 10 minus, this is square root of 5x plus 1. What should I do first? Well, this is pretty simple. I can subtract that from up here. So what's 6 minus 10? Okay. What do you get next? 10 minus 6. Is that negative 4? Okay, that's what I thought. And then this, so I can do away with those. Cancel my negative signs out. Maybe that helps a little bit. Now remember, what do we do at this point? Is we square both sides, right?
Yep.
So even in squaring both sides, that would have taken care of my negative signs. So this gives me 16 equals 5x plus 1. Subtract the 1. And what do you know? I get 15 equals 5x. That divides conveniently and gives me x is 3. Is that what you got?
I got it. Me personally, no.
I got 0.03.
How did you get that?
Problem 23? Oh, no mind, I was in the next one. My bad. Oh, yeah, I did get figured out, yeah.
What about the negative in front of the square root of 5x plus 1?
Well, you had a negative in both cases, so you can cancel those. Or once you square them, it'll go away then too.
Oh, gotcha. That changes everything.
What would the answer to 24 be?
Actually, I mean, the answer would still carry out and give you the same, even if you left it in there. Right?
Yep.
Yes, sir.
Because you would end up having negatives out here in front. Let's just say you left it that way. That negative would carry down through and eventually it would catch up with you here. You just have the opposite signs. And then you still end up with x equals positive 3 as a result. And for number 25, you work that out and find out that x is equal to
3.
3. Again, I think they really like 3 on this page.
What's 24?
Oh, you want to do 24?
No, I want to know the answer. Give me the answer.
What'd you get?
0.03.
You need a fraction for an answer, not a decimal. You can't give me a decimal as an answer on these, that won't be right.
3 over 100.
Wow. No. What's the original problem?
3 over 10?
Kind of scribbly. Is that the original problem?
Yes.
1 over 27? X equals 1 over 27?
So, what do we want to do to simplify this? Anything? Can I do anything to simplify it?
Use cube both sides.
I would think probably that. Cube both sides. What in the world does that give me?
Big.
What's 4 cubed?
64.
4 cubed is 64?
Yes.
64 times
It's 27.
Times the 1 over x.
Yeah, you can. It's 27.
Are we 27?
Yep.
Whatever x equals.
Oh yeah, that's 127.
But you,
Then I just need to do a reciprocal. I get x equals 1 over 27.
Ooh, we get it right.
That's the simpler way to do that.
Get rid of me.
I imagine that if you looked at the steps in the solution key, it's probably not this way. Probably did something with this here and multiplied by a reciprocal or something, but if you remember about reciprocals, you can just do that. This is a great way to do that, probably.
Yeah.
And that should be your answer. Alright, that covers us and gets us through the checkup for the most part. You'll want to finish out the checkup for practice, because as I said, that's a great checkup for practicing for the test, which is coming up 1 week from today. Actually, you can do it earlier if you want.
so do we have to do the rest of the checkup as homework?
The next section, look at what that starts. The next section's super fun.
Yay,
You
next
gotta
section.
finish all the checkup. The next section is where we start having radical signs underneath radical signs. So the next example is going to have a square root of 5, square root of 5, which would have been difficult to deal with before you remembered that you could just turn these into
Just put it in
exponents. You can plug it into your cheatolator. You can bring in exponents into this and make this super simple, because we know that square root of 5 is 5 times 5 to the what? 1/2? That's a square root, which gives me 5 times 5 to the 1/2, all to the 1/2. And then we get to figure out what to do with that next. Remember what happened whenever you multiplied
3.3.
exponents, or raise an exponent to the power of an exponent? Do you add them or multiply them?
Add.
If I had x to the 6 plus x to the 6, and I was adding these, I don't get anything with the exponents. What if it was x to the 6 times x to the 6? I add them, right? X to the 12. What if it was x to the 6 times x to the 3rd? Do I add these?
Multiply.
I multiply them because that's the same as if I had x to the 6 times x to the 6 times x to the 6, which I would add those all up to get x to the 18. So you multiply those two in that case. So here I would multiply those two. And, but I've got to make sure I don't lose something in the translation of doing so. Because this 1/2 is to the power of what? This one and that term. So I have 5 to the 1/2 times 5 to the 1/4, right?
Yes, sir.
And in order to combine those at the end, I need to have the same, because here I know I'm adding my exponents just like I did there, so I can't add 1/2 and 1/4, can I? I can add 2 over 4 to 1/4, and I get 5